Greetings of the day to all of you. The topic of discussion in today's lecture is PWM techniques for three-phase, three-level inverters. We have already completed our discussions on various PWM techniques used in three-phase, two-level inverters. In today's lecture, I am going to discuss with you how different types of PWM techniques are applicable or how they can be implemented or used in multi-level voltage source inverters. So I will write here PWM techniques for multi-level converters. Okay, we can take a 3-level converter, we can take a 5-level converter, or we can take higher level converter, and we can study various PWM techniques on multi-level converters. As you already know, I have already discussed with you in module 1 how multi-level, about the structure of a multi-level converter, how we derive a multi-level converter, what is its structure, and what are its advantages and drawbacks. I have told you that multi-level converters or multi-level inverters are highly suitable for medium voltage, high voltage and high power applications, where series connection of devices in two-level converters is very difficult. Okay, and I have also told you that di by dt and dv by dt stresses in multi-level converters are very low as compared to two-level converters, and for same carrier frequency or for same switching frequency, a multi-level converter gives a better harmonic performance or better harmonic spectrum than a two-level converter. So therefore, for same THD level, the switching frequency of a multi-level converter can be reduced, which will result in reduced switching power losses and higher conversion efficiency. So I will discuss with you three-phase, three-level neutral point clamped inverter. Three-phase, three-level or neutral point clamped inverter. Okay, it's also called diode clamped multi-level inverter, DCMLI. DCMLI means diode clamped multi-level inverter. You already know. So we have a positive DC bus, we have a negative DC bus. Things are like this. This is the DC bus capacitor with voltage across it 0.5 VDC or VDC by 2, and another capacitor has a voltage of VDC by 2. Total DC link voltage or total DC bus voltage is VDC. VDC by 2 plus VDC by 2, that's VDC. This is the midpoint or neutral point of the DC bus capacitors. So as you already know, in simplest form, a three-level inverter can be implemented using single pole, single pole, triple throw switch. I hope you still remember that. I would advise you to revisit, to go through that lecture on multi-level converters in module 1, revise that, and you will find something like this. This is our throw 1, and this is, for example, throw 2, and this is our single pole triple throw switch. This is pole R. It can be either thrown to this, it can be either thrown here, or it can be thrown here, or it can be thrown to midpoint. This is the midpoint of DC bus capacitors. It can be thrown here as well. Okay, so this is single pole triple throw switch. This is one throw, this is another throw, this is another throw. So this is for phase R. Same triple throw switch, single pole triple throw switch can be used for phase Y and then for phase B also. This is pole Y or phase Y. This midpoint of DC bus capacitor can be taken up like this. So similarly we have for phase B. Okay, so this is our single pole triple throw switch. This is pole B. Okay, in two-level converter we have single pole double throw switch, but a three-level converter or neutral point clamped converter is implemented using triple throw switch. Okay, not double throw, not single pole double throw switch, but single pole triple throw switch. And this midpoint of DC bus capacitors is not available for connection in 2-level converters, but it is available for connection in 3-level converters. Let us concentrate on phase R. When pole R is thrown here, the pole voltage VRO is plus VDC by 2. When pole R is thrown here, the pole voltage is minus VDC by 2. And when pole R is thrown at the midpoint, say here, then pole voltage is 0. Okay, so therefore in each phase we have 3 levels of pole voltage, either plus VDC by 2 or minus VDC by 2 or 0. Whereas in 2-level converter we have only 2 levels of pole voltage, either plus VDC by 2 or minus VDC by 2. Since here pole voltage has got 3 levels, plus VDC by 2, 0 and minus VDC by 2, that's why this type of inverter is called 3-level voltage source inverter. How to practically implement these single pole triple throw switches? What about their electronic realization? I've already discussed with you about their electronic realization, and I hope you still remember that. Electronically it can be realized like this. We can have IGBT switches like this. With anti-parallel connected diodes or feedback diodes like this. This is phase R or pole R, and this is your DC bus with DC bus capacitor voltages as plus VDC by 2 across this capacitor and plus VDC by 2 across this capacitor also. And this is the midpoint or neutral point of DC bus capacitors. And this is the total DC bus or total DC link voltage, VDC. Okay, this is phase R. Let us call this switch as SA1, this as SA2, this as SA3, and this as SA4. A stands for phase A. Okay, and then we have clamping diodes. You already know we have clamping diodes also like this. These are the clamping diodes, and they are connected like this. So that's about phase R. Whatever same structure will be there for phase Y and same structure for phase B. Let me complete the connections first. This is SB1, SB2, switch SB3 and switch SB4, and these are the clamping diodes. You can name these clamping diodes also. It's connected to this point. So this is pole or phase Y, and similarly for phase B, something like this. This is SC1, switches SC1, SC2, SC3 and SC4, and these are the clamping diodes. Okay, like this. So this is electronic realization of a 3-phase, 3-level or neutral point clamped converter. Let us concentrate on one phase leg, say phase leg R. When the top switches SA1 and SA2 are turned on, gating pulses are issued to them. They both are on, and the pole R is thrown here, and pole voltage VRO is plus VDC by 2. When the bottom two switches are on, pole is thrown here, and pole voltage is minus VDC by 2. And when middle two switches SA2 and SA3 are on, okay, then through these clamping diodes, this pole is thrown to midpoint of DC bus capacitor, and VRO is 0. So therefore pole voltage will have 3 levels. Top two switches are on, VRO is plus VDC by 2. When middle two switches are on, VRO is 0, and when bottom two switches are on, VRO is minus VDC by 2. Right. So it can be put in the form of a table. Okay, in tabular form it will be something like this. Excuse me. So let us call these switches as switch S1, or let's call this SA1, SA2, SA3, SA4. Okay, we will see their status, and we would like to know what will be the pole voltage VRO. Right, the switching sequence may be like this: 1 1 0 0. 1 means switch is on and 0 means switch is off. So SA1 has a status of 1, that means a gating pulse is available at its gate terminal and it is on. SA2 also has a status of 1, it is also on. Whereas SA3 and SA4, they have a status of 0, so they are off because their gate pulse at their gate terminals is low. Okay, so when SA1, SA2 is on and SA3, SA4 is off, okay, your pole R gets connected to, positive bus, and VRO will be plus VDC by 2. Now the question is, will the switches conduct or will the feedback diodes conduct? That will be decided by direction of current. For example, if the direction of load current is like this, I mean load current is flowing in this direction, because this R, Y, B, they may have a star connected or delta connected load connected. Okay, so if the load current is like this, it is moving out, then obviously this will be the direction of current. Switch S1 will conduct, okay, then switch S2 will also conduct, and then this will be the direction of current. Since SA1, SA2, they are both on, current will flow through SA1, then SA2, and it will move like this. Okay, but on the other hand, if the direction of load current is like this, I mean if load is entering, okay, then obviously even if gating pulses of these two switches are high, they will not conduct because direction of current is reverse. The IGBTs conduct only from top to bottom, collector to emitter. They will not conduct from bottom to top. That means they will not conduct from emitter to collector. Okay, so for this direction of load current, the anti-parallel connected diodes or feedback diodes have to conduct. So they have to conduct like this. Okay, so this will be the direction of current. So direction of current will decide whether IGBT switches are conducting or feedback diodes are conducting. For this direction of current, SA1, SA2 IGBT switches will conduct, and they will conduct the current. And if the direction of current is opposite, then feedback diodes will conduct and they will conduct the current like this. Okay, so and what will be VRO? So whether SA1 or SA2 are conducting or DA1 and DA2 are conducting, R is connected to positive DC bus, okay, and pole voltage VRO is plus VDC by 2. Okay, right? So the switching status may be now like this: 0 1 1 0. Okay, for this switching status, let me erase these arrows showing direction of currents, because now we will consider a different switching state. Okay, this is DA1, this is DA2, this is DA3, and this is DA4. Now middle two switches are, their gating pulses are high, SA2 and SA3. Okay, so when middle two switches have high gating pulses, direction of current may be like this, and when direction of current is like this, the current will flow like this through this clamping diode and then through switch SA2, because SA2 is conducting like this. Okay, so for this direction of current, if the load current is like this, so this clamping diode and IGBT switch SA2 will conduct like this. And R is, you can see through this switch and through this diode, R is connected to midpoint of DC bus. And what is DC VRO? VRO will be 0. On the other hand, if the direction of current is reversed, that means if current is in this direction, so obviously then SA2 cannot conduct. Okay, because it cannot conduct from emitter to collector. DA2 can also not conduct. Now DA2 will conduct only if this diode conducts, but this diode will not allow current to flow from cathode to anode. So the only path for the direction of current is like this. Since SA3 has high gating pulse, so SA3 will conduct, and then this clamping diode like this. So this will be the direction of current. So therefore, if the current is coming out of phase R, I mean if the direction of load current is like this, then this will be the direction of current. If the direction of load current is opposite, reverse, then this is the direct path of the current. Okay, so whether current is in this direction or current is in this direction, pole R in both the cases is connected to midpoint of DC bus, and pole voltage VRO will be equal to 0, right? Now third switching state may be 0 0 1 1. For 0 0 1 1, I will have to again erase these current directions. Okay, fine. So that means SA3 and SA4 have high gating pulses. So now again direction of current may be like this. If direction of current is like this, then these diodes will conduct DA3 and DA4, they will conduct like this, and they will conduct the current like this. Okay, and if the direction of current is opposite, I mean if this is the direction of current, then IGBT switches will conduct, because diodes cannot conduct from cathode to anode. IGBT switches, they have high gating pulses, they can conduct from collector to emitter. So this will be the direction of current through IGBT switches like this. Okay, now whether the direction of current is like this or the direction of current is like this, pole R or phase R is connected to negative DC bus, and what is VRO, pole voltage, in both the cases for both directions of current? VRO is minus VDC by 2. That's it. So therefore I have shown you the switching table. The switching status may be 1100, for which case pole voltage VRO is plus VDC by 2, 0110 for which VRO is 0, and 0011 for which VRO is minus VDC by 2. That's it. So this we have already discussed, and this is just a revision of or review of what we have already learned in module 1 about multi-level converters. So therefore if we see instantaneous pole voltages, line voltages, and line to neutral or phase voltages. Instantaneous pole voltages, line voltages, or phase voltages. Let's first of all take pole voltages. So VRO, say phase or phase leg or pole voltage VRO will be plus minus VDC by 2, VDC by 2, or 0. I mean it can be plus VDC by 2 or minus VDC by 2 or 0. So it has 3 levels. That's why it's called 3-level inverter, 3-level voltage source inverter. So it has got the name from the status of pole voltages, because all the 3 pole voltages have 3 levels, plus VDC by 2, 0, minus VDC by 2. So this type of inverter is called 3-level voltage source inverter, right? What about line voltages? Line voltages are VRY equal to VRO minus VYO. Similarly, VYB will be equal to VYO minus VBO, and VBR will be equal to VBO minus VRO. And let me tell you the line voltage. Let's take line voltage VRY. It will have 5 levels. It will be either plus VDC by 2, or it will be minus VDC by 2, or it will be plus VDC or minus VDC, or it will be 0. Okay. So for example, if VRO is VDC by 2, VYO is minus VDC by 2. So VRY is VRO minus VYO, that is plus VDC by 2. On the other hand, if VYO is plus VDC by 2 and VRO is minus VDC by 2, so it will be, if VRO, so let me repeat it. If VRO is plus VDC by 2, VYO is 0. Then line voltage VRO is VDC by 2 minus 0, so it is plus VDC by 2. On the other hand, if VYO is plus VDC by 2 and VRO is 0, then line voltage VRY will be minus VDC by 2. And then if VRO is plus VDC by 2, VYO is minus VDC by 2, then line voltage is VDC by 2 minus VDC, that's plus VDC. On the other hand, if VYO is VDC by 2 and VRO is minus VDC by 2, VRY will be minus VDC by 2 minus VDC by 2 minus VDC. And if VRO is VDC by 2 and VYO is also VDC by 2, then line voltage VRY is 0. And if VRO is and VYO both are minus VDC by 2, then also it will be 0. Or if VRO is 0, VYO is also 0, then also line voltage will be 0. So we have already discussed in details in our module 1. So line voltage will have 5 levels. It will be either plus VDC by 2 or minus VDC by 2 or plus VDC, minus VDC or 0. So it will have 5 levels. But we do not call it 5-level inverter, although you will find some limited literature where this type of inverter is called 5-level inverter based on the levels in the line voltage. Okay, because line voltage has 5 levels. Some literature you may find where it's also called 5-level inverter, but most of the literature calls it 3-level inverter based on the voltage levels in pole voltages. And since pole voltage has 3 levels, that's why it's mostly called 3-level voltage source inverter. What about phase voltages? Say VRN, phase voltage is 1 by 3 times VRY minus VBR. We already know it. Similarly, line to neutral voltage VYN is equal to 1 by 3 times VYB minus VRY, and phase voltage VBN is equal to 1 by 3 times VBR minus VYB. Okay. So therefore, if you see the phase voltages will have 9 levels. For example, phase voltage VRN will have, it may be plus minus 2 by 3 VDC, it may be plus minus VDC by 2, it may be plus minus VDC by 3, it may be plus minus VDC by 6 or 0. Okay, so plus VDC, plus 2 by 3 VDC or minus 2 by 3 VDC, plus VDC by 2 or minus VDC by 2, plus VDC by 3 or minus VDC by 3. Similarly, plus VDC by 6, minus VDC by 6, and 0. So how many levels are these? 2 plus 2, 4 plus 2, 6 plus 2, 8, 9. So phase voltage has 9 levels. If you simulate this 3-level inverter, you'll find that pole voltages will have only 3 levels. That's why it's called 3-level voltage source inverter, whereas line voltages will have 5 levels and phase or line to neutral voltages will have 9 levels, right? So for phase voltage VRL equal to 2 by 3 VDC, we can have only one possibility. Only one possibility is there, and that possibility is that VRY should be equal to VDC and VBR should be equal to minus VDC. What is our VRN? By the way, VRN is 1 by 3 times VRY minus VBR. This is the formula. What is VRY? Put VDC. So it is 1 by 3 times, if VRY is VDC, minus VBR is minus in minus plus VDC. So VDC plus VDC is 2 VDC. So it is 2 by 3 VDC. So this is the only possibility that VRN will be equal to 2 by 3 VDC. Okay. It has only one switching state. There is line voltage VRY should be plus VDC and VBR should be minus VDC. That will give phase voltage VRN equal to 2 by 3 VDC. Only one possibility is there. Okay, there is no redundancy. On the other hand, for VRN equal to VDC by 2, if you take VRN equal to VDC by 2, you have more possibilities. For example, VRY should be equal to VDC and VBR should be equal to minus VDC. Okay. We verify it. VRY should be VDC and VYB should be minus VDC. Minus VDC by 2. So therefore, what is VRN? VRN by formula is 1 by 3 times VRY minus VBR. Put VRY equal to VDC, so it is 1 by 3 times VDC minus VBR is plus minus VDC by 2. So minus into minus is plus VDC by 2. So 2 plus 1 is, it is 1 by 3 into 3 by 2 VDC. 3 and 3 goes, so it is VDC by 2. This is one possibility. But you may have another possibility. Another possibility may be that VRY is equal to VDC by 2 and VBR is equal to minus VDC. So therefore VRN is 1 by 3 times, what is VRY? VRY is VDC by 2, minus into minus is plus VDC. So this is 3 by 2, 1 by 3 into 3 by 2 VDC. 3 and 3 again goes, so it is VDC by 2. So therefore, if you want VRN equal to VDC by 2, you have two possibilities. One possibility is that line voltage VRY is plus VDC by 2 and VBR is minus VDC. Another possibility is that VRY is plus VDC and VBR is minus VDC by 2. Similarly, if you if you want VRN equal to VDC by 3, you have more than two possibilities. VDC by 6 has more number of possibilities. You can try yourself. And highest number of possibilities is if VRN you want equal to 0. So VRN equal to 0 will have highest possibilities. highest possibilities, which also means redundancies for VRN equal to 0. So you have many switching combinations which will give you VRN equal to 0. So it has highest number of redundancies. Since a particular phase voltage level can be, created by more possibilities, I mean, different switching states produce same phase voltage level. So this gives us an idea that a three-level inverter the PWM techniques of three-level inverter can be designed with more switching possibilities. So PWM techniques will have redundancies. I mean, there is redundancies in switching states, which will give us more degree of freedom for creating certain voltage levels. Okay, so that's about this. Now the question is, I told you at the beginning of this lecture, and I told you in module while discussing multi-level converters in module 1 also, that this multi-level converters give less error voltage. They give better harmonic spectrum of voltage as well as current. Okay, let us assume that we want an average pole voltage, VRO average. We want it equal to 0.25 VDC. Okay, that means I want it equal to VDC by 4. So I may produce average pole voltage equal to 0.5 VDC by either 2-level inverter or by 3-level inverter. By 2-level inverter, if I use 2-level inverter, so it will be like this. It is plus VDC by 2, ये 0 है, and this is minus VDC by 2. Okay, so what I will do, I will keep it on for a larger period of time. And I mean, I will keep top two switches on. That is SA1 and SA2 will be on for a larger period of time, so that pole voltage VRO is plus VDC by 2. And I will keep bottom switches on for less time. So during this period, bottom switches SA3 and SA4 are on. When two bottom switches are on, just you have seen few minutes back, when two bottom switches are on, pole voltage is minus VDC by 2. And when two top switches are on, pole voltage is plus VDC by 2. In order to get average pole voltage equal to 0.25 VDC, which is something here, this is 0.5 VDC. I will keep top two switches on for more time, so that my pole voltage is plus VDC by 2 for more time, and bottom two switches will be kept on for less time, so that pole voltage equal to minus VDC by 2 is there for less time. So what will be average voltage? Average voltage will be positive because plus VDC by 2 is there for more time and minus VDC by 2 is for less time. So you can produce an average pole voltage, VRO average, equal to 0.25 VDC. It's not 0.5 VDC, it's 0.25 VDC. This is how two-level inverter can create. But there is a huge error. For example, your desired output voltage is 0.25 VDC and your actual, the error is, this is the error voltage, V error. Okay, so this is minus VDC by 2 and this is your desired output voltage, 0.25 VDC, and this is the error. The same thing can be achieved if you use 3-level inverter. This is if you use 2-level voltage source inverter. Now if I use 3-level voltage source inverter for producing an average pole voltage of 0.25 VDC, it will be like this. This up top two switches will be on. Okay, I'm sorry here, since I am considering 2-level voltage source inverter, we have only two switches, top switch and bottom switch. I should not have written SA1, SA2. I should have written SA1 and this is SA2. Because a 2-level inverter has only two switches per phase leg. This is top switch is switch SA1, this is SA2. So SA1 will be on for more time. It will give pole voltage plus VDC by 2 for more time, and bottom switch SA2, we can call it SA2, it's on for less time, so that pole voltage is minus VDC by 2 for less time, and average pole voltage is VRO average equal to 0.25 VDC. The same thing can be achieved by 3-level voltage source inverter. 3-level voltage source inverter. For 3-level voltage source inverter, this is our plus VDC by 2 and it's then 0. And this is, for example, minus VDC by 2. But what we are doing, we are keeping top switches on for, these are top switches, SA1, SA2. They are on for some time, and they give a pole voltage VRO equal to plus VDC by 2. And middle two switches, that is SA2 and SA3, they are kept on for some time, equal amount of time. Okay, equal amount of time, so that the pole voltage is 0. Because we know that when middle two switches are on in 3-level inverter, the pole voltage is 0. So this is your then average. Since duty ratio is 50% here, positive voltage is there for, say, time t by 2, and 0 voltage is there for time t by 2 again. So duty ratio is 50%. The average pole voltage, VRO average, you will get equal to 0.25 VDC. Okay, and what is the average voltage? What is the error? Error is very, very small. Here error is very large. This is what you desire and this is what you apply. Error is very large. Here error is very small because you are not applying negative DC, pole voltage at all. You are switching between positive pole voltage and 0 pole voltage. So this reduces the error, and this explains why 3-level inverters give better harmonic spectrum or better harmonic performance of the inverter. Fine. Let us now discuss PWM techniques for 3-level voltage source inverter. I will write here Sine Triangle Pwm for a neutral point clamped inverter. So called neutral point clamped inverter, or it's called 3-level inverter also. Sine Triangle Pwm. We know that for 2-level voltage source inverter, we have 3 sinusoidal modulating waves, like we have MR, this is MR, we have MY, and this is third modulating wave, MB. And these modulating waves are compared with high frequency triangular carrier wave like this. This is our high frequency triangular carrier wave. Large number of carrier wave cycles are there depending upon the switching frequency. Then the comparison of 3 sinusoidal modulating waves with high frequency triangular carrier wave will independently modulate the 3 phase legs, phase leg R, phase leg Y, phase leg B, and it will produce instantaneous average pole voltages, instantaneous average phase voltages, instantaneous average line voltages, which are sinusoidally varying. So at the output of inverter, we will get average, instantaneous average AC voltages, right? This is about 2-level inverter, 2-level voltage source inverter. In 3-level voltage source inverter, we have to use 2 level shifted carriers. Okay, I will note down here 2 level shifted. This is the first modulation technique. 2 level shifted carriers have to be used for 3-level inverter, for neutral point clamped inverter. Something like this. Please try to understand. Instead of 1 carrier, you have to use 2 carriers, and those 2 carriers are level shifted carriers. Let me first of all draw modulating waves. This is sinusoidal modulating wave MR. Let us assume modulation index is 0.8, so its peak value is plus 0.8 and minus 0.8. This is MR. Similarly, we have MY like this. This is modulating wave MY, and we have third sinusoidal modulating wave MB like this. This is MB. Now, instead of having 1 high frequency carrier, we will use 2 level shifted carriers. Okay, so for example, this is the peak value of carrier wave VP, and VP is equal to 1.0, and this is negative peak, minus VP. Minus VP equal to minus 1.0. I will write here minus 1.0. So I will have 2 triangular carrier waves which are level shifted. 1 triangular carrier wave is like this. So it will not have negative excursion, it will have only positive excursion. It will be plus 2, 3, let's take 5 carrier waves in one half cycle. Okay, similarly 1, 2, 3, 4 and 5. Similarly 1, 2, 3, 4, 5. So this is carrier 1. Let me call this carrier 1. So the 3 modulating waves are compared with carrier 1. And we will have another carrier wave. We'll have another carrier wave which will be in phase with this carrier wave but level shifted. Level shifted means that will have a negative peak of -1. So that will change from 0 to -1. This is changing from 0 to +1 continuously. That will change from 0 to -1. So you have to understand that. So for that purpose, I will take these projections downwards for accurate waveform. So my other carrier wave will start from here. It will be in phase with this carrier wave but level shifted. See, you can see it's exactly in phase with this, but it is level shifted. This has a level of +1, this has a level of -1. So level, that's why these carriers are called level shifted carriers. They are in phase but level shifted. 3, 4, 5, 6. So you can continue like this. So this is carrier 2. That's carrier 1, this carrier 2. Now what you do, positive half cycle of MR, positive half cycle of MY and positive half cycle of MB modulating waves is compared with carrier 1 and it generates the gating pulses for the switches, IGBT switches. Similarly, -MR, -MY and -MB, they are compared with carrier 2 and for negative half cycles also they generate this what we call as gating pulses for the inverter switches. Okay, this is how to use it. I will discuss with you. See, at any instant of time, for example, if you take this instant to this instant, carrier 1 or a modulating wave, let's consider phase leg R. This is our phase leg R. It has 4 switches. I will consider only phase leg R for better understanding. I will not consider other phase legs because same procedure follows or applies for other phase legs. And this is our, for example, plus VDC by 2 and plus VDC by 2, VDC by 2, VDC by 2, and these are clamping diodes like this. This is 0. This is, say, for example, S1, S2, S3, S4. And you can see from this instant to this instant, modulating wave MR is greater than both carriers. It's greater than carrier 1, it's greater than carrier 2 also. So the top 2 switches will be on and pole voltage will be plus VDC by 2, right? During this interval of time, on the other hand, you will see here, sorry, I'm considering phase leg R. You can now see MR is less than both carriers. It's less than carrier 1, it is less than carrier 2 also. So it will issue gating pulses to bottom 2 switches, S3, S4, and your pole voltage is minus VDC by 2. And during in between means somewhere here, say for example here, my modulating wave MR is less than carrier 1, but it is greater than carrier 2. So middle 2 switches S2 and S3 will be on and pole voltage VRO will be 0. Similarly, at this instant of time, for example, at this instant of time, my modulating wave, this modulating wave, MR, where is MR? Yeah, here. Here you can see MR is, here you can see, it is less than carrier 1, but it is more than carrier 2 because carrier 2 more negative hai. So it is more than carrier 2. So that will also again put middle 2 switches on. So therefore, when a particular modulating wave, say modulating wave MR is greater than both the carriers, top 2 switches will be on and pole voltage VR will be equal to plus VDC by 2. When the modulating wave MR is less than both the carrier waves, for example, from this to this, the bottom two switches will be on and pole voltage VRO will be equal to minus VDC by 2. And when modulating wave is less than carrier 1 but greater than carrier 2, or less than carrier 2 and greater than carrier 1, then middle two switches are on, and at that time pole voltage is equal to 0. This is the logic. Okay, this logic you can implement using MATLAB Simulink software, or you can do it through programming. You can generate two level shift carriers like this. You can compare them with three sinusoidal modulating waves like this, and using this logic, that means, say for example, if MR is greater than both carriers, greater than carrier 1 as well as carrier 2, then switch S1, S2, their gating pulse should be high, and VRO at that time will be plus VDC by 2. On the other hand, when MR is less than both carriers, its amplitude is less than both carriers, bottom two switches will be given gating pulses S3, S4. They will be put on, and your VRO will be minus VDC by 2. On the other hand, if MR is greater than carrier 1 but less than carrier 2, or it is greater than carrier 2 but less than carrier 1, then in that case middle two switches will get control pulses or gating pulses. S2, S3 will be on, and your pole voltage VRO will be equal to 0. You can implement this logic through Simulink software or MATLAB programming. You can create an M file, or you can use Simulink software, and you can generate the gating pulses using this logic for phase leg R switches, phase leg Y switches, and phase leg B switches by comparing MR, MY, MB with these level shifted carriers, and your inverter will produce 3-level. It will act as a 3-level or neutral point clamped or diode clamped 3-level inverter. And at the output, you will get pole voltages which will have 3 levels, line voltages will have 5 levels, and phase voltages will have 9 levels. So this is how you can implement a 3-level voltage source inverter. Okay. Now, after this, we have to discuss phase shifting. I mean, we can go for phase shifting also. I will write here phase shifting. This is second type of PWM technique, Sine Triangle Pwm technique. That is phase shifting in level shifted carriers. I mean, now you have two level shifted carriers. You can phase shift one of the level shifted carrier. This is one carrier, this is another carrier. They are right now in phase. They are level shifted but in phase. So another type of sine triangle modulation which has been reported in the literature is that you just phase shift this bottom carrier by maybe 20 degrees to 30 degrees. You can phase shift it. आप इसको shift कर लीजिए ऐसे. You shift it. I am showing this phase shifting by red color pen. You can continue like this. Now you can see this bottom carrier, carrier 2, is not in phase with carrier 1. It is out of phase with carrier 1 by a phase angle phi. It may be 20 to 30 degrees. It will again make your inverter to operate as a 3-level inverter, but it will have different harmonic spectrum. I mean, THD may get better or worst. I mean, both possibilities are there. The inverter output voltage may have better THD, or it may have worse THD. Okay. The third method is to have out of phase level shifted carriers. Now, third category of sine triangle PWM for 3-level inverters is out of phase, completely out of phase, not phase shifted. I mean, phase shifted by 180 degrees, out of phase. Out of phase level shifted carriers. Out of phase level shifted carriers. Let us draw the carriers again along with the modulating waves. So we have 3 modulating waves. MR, this is modulating wave MR, right? Let us assume modulation index is 0.8 again. So its amplitude is minus 0.8 plus 0.8. Same is the case with MY and MB. So this is our MY modulating wave. This is modulating wave My and this is modulating wave Mb. Now we have two carriers. We have carrier 1 and carrier 2. Okay, this is 1.0 peak value of carrier wave, 1.0 positive peak, and this is negative peak, minus Vp, which is equal to minus 1.0. So I have a level, I have carrier 1 like this, 1, 2, 3, 4, 5. Okay, for 1/2 cycle of MR, I have 5 cycles of carrier. So you can continue like this, 3, 4, and 5. Similarly, 1, 2, 2, 3, 4, 5. So this is again carrier 1. Let's call this C1. Now carrier 2 will not be in phase with carrier. Carrier 2 will be level shift, no doubt, but it will not be in phase. It will be out of phase like this. Let me show you how out of phase carrier is generated. Let me drop these projections so that I can draw the carrier 2 C2 properly. So my carrier 2 is level shifted, but it is not in phase with carrier 1. It is out of phase. You see, it's out of phase. So this is carrier 1 C1. This is carrier 2 C2. So you can see out of phase with each other by 180 degrees. So you can continue like this. So they are level. The two carriers C1 and C2 are level shifted, and they are simultaneously they are out of phase with respect to each other. So you can continue drawing the carrier like this. I advise you that when you also draw these waveforms, carrier waveforms at your places, at your homes, use different color of pens. Okay, so this is C1, C2. Rest, the logic is same. Whenever any modulating wave is greater than both the carriers, top two switches will be on and pole voltage will be plus VDC by 2. Whenever the particular modulating wave is less than both the carriers, the bottom two switches of a particular phase leg will be on, and that particular phase, this pole voltage will be minus VDC by 2. And whenever the particular modulating reference wave or sinusoidal modulating wave is greater than one carrier but less than another carrier, and middle two switches will be on, and that will make your pole voltage equal to 0. Same logic. Now, should we go for in-phase level-shifted carriers or out-of-phase level-shifted carriers? If you see the literature and if you try simulating both these, PWM techniques using MATLAB software or any other software, first of all, you can take in-phase level-shifted carriers, which I have discussed just few minutes back, and you use FFT block and find the THD of inverter output voltage and current, and then use this PWM technique, sinusoidal PWM technique, with out-of-phase level-shifted carriers like this, and simulate your inverter again, and you will see that out-of-phase level-shifted carriers, this type of sinusoidal PWM technique with out-of-phase level-shifted carriers, it gives better harmonic spectrum or better harmonic performance. Better harmonic performance. Better harmonic performance means lower THD than in-phase level-shifted carriers, which we have discussed just few moments back. So literature also will tell you, if you read the research publications, research papers, literature or books, that will also tell you that this sinusoidal modulation method is better than in-phase level-shifted carriers, the other modulation method. Okay. So that is about this. And fourth type is, instead of using two carriers, can we use only one carrier, single carrier? Yes, that's also possible. I will now note down single carrier PWM technique. Single carrier PWM technique. Because whether it is in-phase level-shifted carriers or out-of-phase level-shifted carriers or phase-shifted level-shifted carriers, you have to use two carriers. Can we do with only one carrier, as we have been doing in two-level inverters? Answer is yes. Let me show you how we can do that. That's also reported in the literature. You can see the books and you can see the research literature, the papers, research papers. There it has been reported. The single carrier PWM technique has also been reported. Single carrier PWM technique. will again draw, let me draw only one modulating wave because I want to just explain what do you mean by single carrier PWM. This is 0.8 and this is minus 0.8. Okay, so I have positive peak of carrier Vp, which is 1.0, and negative peak of another carrier minus Vp, which is equal to minus 1.0. Let me first of all show you two level shifted in phase carriers like this. 1, 2, 3, 4, and 5. 5 in positive half cycle and 5 in negative half cycle. 1, 2, 3, 4, and 5. Okay, so this is my carrier 1, and my carrier 2 is like this, that is level shifted, and but it is in phase. I can show you in phase, I can show you in fact out of phase also, but let me draw in phase because ultimately then we will use only one carrier. This is my another carrier, level shifted carrier, in phase level shifted carrier. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is carrier 2. It is possible that we can shift this. See, this is positive MR, this is negative MR. We can shift this negative MR to, in the positive half cycle like this. For example, ये pi है इसका. Just raise it. When we raise it and invert it. Sorry, don't invert it, just raise its level. इसको ऊपर ले जाइए. It's in the negative half cycle. So shift it to the positive half cycle. When you shift it to the positive half cycle, it will be something like this. So what I am doing, so as far as this MR is concerned, it's negative half cycle, I am shifting above. Okay, so then this, my modulating wave MR becomes like this. This is not my MR now. My MR is like this and then like this. So that way, what you will do, you don't need this carrier, you don't need negative carrier, because negative MR you have shifted to the positive side. Same is the case with MY, same is the case with MB. So you can rub this off. Okay, so therefore you have only one carrier. Let me not call it carrier 1. I have only one carrier. We call it carrier 1. Sorry, let me call it carrier because I have only one carrier. And my modulating wave MR is like this. Similarly, I can show MY, I can show MB. Okay, so logic is same. Whether we are in the positive half cycle or we are in the negative half cycle, whenever MR is greater than carrier wave, top two switches is on, top two switches will be on, otherwise bottom two switches will be on, and I mean middle two switches can also be, we can think of middle two switches being on. If you consider, I mean, both the carriers, and if you are, modulating wave is greater than one carrier and but less than another carrier, middle two switches will be on. Okay, so this is how you can generate gating pulses with single carrier PWMs. This single carrier PWM has also been reported in the literature. This is similar to two in-phase carriers, in-phase level shifted carriers, but with one modulating, with one carrier. I mean, only one carrier. We are not using another carrier. We are not using level shifted carrier. We are using one carrier. So this is called single carrier PWM technique. Okay. Now, it's very important for you to understand the switching sequence. Let us understand switching sequence with out of phase level shifted carriers. Out of phase level shifted carriers. Let us take one carrier cycle. See, this is my peak voltage of carrier Vp, which is plus 1.0, and this is minus Vp, it is minus 1.0. Okay, ये बीच में 0 है. This is my omega t axis. This is omega t axis 0. I will now consider two carriers, and I will take half of the carrier. So this is one, and another carrier is level out of phase level shifted. Sorry, it's like this. So you can call this carrier 1, this is carrier 2. Actually it is like this, pura carrier agar aap leke, this is carrier 1 and this is carrier 2. But what I am doing, I am taking only half of the carrier, जिसको हम subcycle TS कहते हैं. This is one subcycle, this is another subcycle. This is my carrier 1 and this is carrier 2. Similarly, this is subcycle TS, this is subcycle TS. I am taking this subcycle, half carrier period, TS. So this TS is half carrier period. Half carrier period. Full carrier period is like this, TS plus TS, 2TS. Half carrier period is only this and this. And since these are level shifted and out of phase carriers, just like this. Now these have to be compared with modulating waves. Let us compare these two carriers with modulating wave. Say for example, I have modulating wave MR, okay, and then I have modulating wave MY, and I have another modulating wave MB. I am taking constant modulating wave because carrier frequency, I repeat, is very high. Your switching frequency may be 10 kilohertz, 20 kilohertz or more than that, and if you take half of the carrier, for that half of the carrier, modulating signals MR, MY, MB, which are basically sinusoidal modulating signals, they will appear constant for such a small period of time, TS, half carrier period. So this is MR, this is MY, this is MB. Okay, now first switching will occur somewhere here. This is the first switching. Now let me write phase R switching, phase Y switching, R, Y and B. Now we can see, you have to see intersection of carrier wave with modulating waves. आपकी modulating wave MY ये है and your carrier C2 intersects MY somewhere here. ये आपका पहला switching instant. You can see from here to here, if you consider MR, यहाँ से यहाँ तक अगर आप देखेंगे, आप MR consider करेंगे, modulating wave MR is greater than both carrier waves, C1 as well as C2. So that means top two switches of phase leg R will be on. So therefore this will have a status of plus. Plus means pole voltage VRO will be equal to plus VDC by 2 because top two switches will be on. Yes, about phase leg R. What about phase leg Y? Phase leg Y में आप देख सकते हैं, what is MY? MY is less than both the carriers. It is less than, you can see, this is your MY. MY is less than carrier 1, it is less than carrier 2. So phase leg Y के bottom those switches on हो जाएंगे and pole voltage will be minus VDC by 2. So it will have minus status. What about MB? MB may be यही है because MB is less than both the carriers. It will also have minus status. तो ये हो गया पहला switching. Next switching will take place here क्योंकि दूसरा intersection यहाँ हो रहा है carrier और modulating wave का. This is the next. Now you can see during this period again MR is greater than both the carriers, so it has positive status. Phase leg R has positive status, but that means top two switches of phase leg R will be on and pole voltage will be plus VDC by 2. What about phase leg Y? MY, you can see MY is less than carrier 1, but it is greater than carrier 2. So I have told you whenever any modulating signal is greater than one carrier wave but less than another carrier wave, the middle two switches will be on and pole voltage will be 0, so it will give 0 status to phase leg Y. And what about MB? MB आप देख सकते हैं, it is less than C1 but it is greater than C2. So ये भी आप oh sorry, I am here. MB MB is less than both. It is less than C1 as well as C2, so it will be minus, plus 0 minus. And then we have final switching, third switching, not final switching, which is तीसरा intersection यहाँ हो रहा है carrier और modulating wave का. यहाँ पे आप देख लीजिए आप. During this interval, MR is again greater than both the carriers, so phase leg R has plus status. What about MY? MY is greater than C2 but less than C1, so it is 0. What about MB? MB is कहाँ है MB? हाँ, MB is greater than MB is greater than 1 carrier, less than, so it will have a status of 0. Okay, so plus 0, 0. Because it is greater than this carrier, but it is less than this carrier. Sorry, it is greater than this carrier, but less than this carrier, 0. And finally, this is the last switching instant. यहाँ पे आप देख सकते हैं MR has now become less than both. It has become less than this carrier, but it is greater than this carrier, so 0 status. MY is greater than this, but less than this, 0. MB is also greater than this, but less than this, 0. So therefore, मेरी switching sequence कैसे होगी? So what will be my switching sequence? Let me show you the switching sequence. Switching sequence will be in one subcycle. ये पहला आपका subcycle TS है. In one subcycle, switching sequence is plus minus minus, plus R plus Y minus B minus, followed by plus 0 minus, followed by plus 0 0, followed by 0 0 0. ये एक subcycle है. And in the next subcycle, we know reverse order. First 0 0 0, then I need more space. Let me show it here. Plus minus minus, followed by plus 0 minus, followed by plus 0 0, followed by 0 0 0. This is one subcycle. Yes. In another subcycle, in the reverse order, I mean first 0 0 0, then this plus 0 0, then plus 0 minus, then plus minus minus. This is another subcycle. This is just like same as in case of two-level voltage source inverter. Two-level voltage source inverter, maybe switching sequences like this. I mean, their switching sequence, there we don't have 0, we have plus and minus only, because pole voltage is only 2 levels. Here it's like this. So 1 2 3 4 5 6 7 8 switchings in one carrier cycle, which is equal to 2 TS. Subcycle plus subcycle. इसको अगर आप space vector domain में transfer करेंगे, let me first of all show you space vector domain. Let me tell you the space vector pulse width modulation for multi-level inverters. That topic will be taught to you by Dr. Tabish, because this space vector SVPWM for multi-level inverters is overlapping between my subject and her subject. Since I have already taught you in details SVPWM for two-level inverters, I have requested her to discuss SVPWM technique for multi-level inverters. So she will take a couple of lectures and she will discuss space vector PWM technique for multi-level inverters. Okay, and here I would like to show you the space vector diagram, SV diagram for 3-level inverter will be something like this. I will not explain that. That will be explained by Dr. Tabish. Please bear with me. It will be something like this. See, आपका vector 1 है with switching sequence plus minus minus, then space vector 2 plus plus minus. ये अभी तक तो वैसे है जैसे 2-level inverter में है. Then space vector 3 minus plus minus, then space vector 4 with minus plus plus, space vector 5 with minus minus plus, and space vector 6 with plus minus plus. Okay, let me join these. It will form a hexagon like this. It will form a hexagon like this. Okay, इसमें 3-level inverter में, in addition to these 6 active voltage vectors, 1 2 3 4 5 6, you will have 0 voltage vector, plus plus plus, then 0 0 0, minus minus minus. If you remember in 2-level inverters, we had 0 switching state, either plus 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 or minus minus minus. But in 3-level inverter, we have plus plus plus, this is null vector, minus 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 also gives null vector, and 0 0 0 also gives null vector. The 0 is absent in 2-level inverter. And then इसमें बीच में भी एक वेक्टर आ जाता है 3-level इन्वर्टर में, एक वोल्टेज स्पेस वेक्टर आधे मैग्नीट्यूड, इसका मैग्नीट्यूड है VDC, एक वोल्टेज स्पेस वेक्टर जिसका मैग्नीट्यूड VDC/2 है, वो दैट्स समवेयर हियर इन द मिडल ऑफ दिस voltage vector along alpha axis. Okay, उसकी switching sequence है plus 0 0 or 0 minus minus. I mean, if you have a switching sequence of plus 0 0 or 0 minus minus, both the switching sequences will produce same voltage space vector, which is shown by this arrow. आपका एक और voltage space vector यहाँ पे आ जाएगा, जिसकी switching sequence, which will be produced by this switching sequence, plus 0 minus in the middle. Your another voltage space vector will be in the middle here, somewhere here, इसके बीच में, which it will be produced by voltage space vectors plus 0 and 0 0 minus. Those switching states same vector produce करेंगे. And if you join these, then you will have 4 triangles. This is your sector 1. In 2-level inverters, sector 1 had only 1 triangle. You did not have these middle voltage vectors. But in 3-level inverter, in addition to these external voltage vectors, you have these middle voltage vectors also. And when you join them, in sector 1 you have 4 triangles, sub triangles. ये बड़ा triangle है जिसको sector कहते हैं, इसमें छोटे 4 triangles है, 1 2 3 4. These are called regions. So sector 1 has 4 regions, 1 2 3 4. Similarly, sector 2 also will have 4 regions. You can continue like this. Sector 3 will also have 4 regions. ये देखिए 1 2 3 4. This will also have 4 regions like this. 1 2 3 4. This will also have 4 regions. This will also have 4 regions like this. So each sector is divided into 4 regions: region 1, region 2, region 3 and region 4. And your rotating reference vector at any instant of time, Vref, may be in any one of the regions in a particular sector, depending upon the modulation index. For example, in sector 1 it may be in region 1 at any instant of time, or it may be in region 2 or region 3 or region 4, depending upon modulation index. Similarly, in sector 2 also it may be in any of the regions: sector 3, sector 4, sector 5 and sector 6. I am showing the middle voltage vector switching sequences here for sector 1 only. I am not showing for other sectors. Dr. Tabish will explain to you all the switching sequences which produce these middle voltage vectors for other sectors also. I am skipping that part here because that part I have requested her to discuss with you people. Okay. So therefore, with respect to the space vector diagram, if I consider this switching sequence, let me see how does it look like. This is a space vector 1 with switching sequence plus minus minus. In sector 1, this is space vector 2 with switching sequence plus minus, right? और आपका ये है plus 0 0 0 minus null vector. Your null vector is produced by 3 switching states. Either plus means all the top 2 switches of all the 3 phase legs are on, or 0 0 0 means the middle switches of all the 3 legs are on, or minus means the bottom switches of all the 3 phase legs are on. So these 3 switching states will produce null vector. Okay, and then you have a vector here, somewhere here, middle में एक vector है which will be produced by this switching sequence, plus 0 0 or 0 minus. Both the switching sequences will produce same voltage vector, ये voltage vector. Similarly, एक यहाँ बीच में होगा which will be produced by one switching sequence plus 0 minus. एक यहाँ पे होगा which will be produced by 2 switching sequences plus 0 or 0 0 minus. These 2 switching sequences will produce this voltage vector. ठीक है, अब आपकी switching sequence यहाँ क्या है? Let me show you all the 4 regions. So this is region 1, region 2, region 3, region 4 in sector 1. ये आपका sector 1 space vector diagram. So this is alpha, and we already know this is beta axis. This is sector 1, and sector 1 we have divided into 4 small sub triangles which are called regions: region 1, region 2, region 3 and region 4. My first switching sequence in a subcycle is plus minus. Where is plus minus? Plus minus is here. So my what will my controller do? It will apply this voltage vector plus minus for time interval, say t1. Then it will apply plus 0 minus. Where is plus 0 minus? So it will then apply this voltage vector. So it will jump from this to this for time interval t2. Then it will apply plus 0 0. Where is plus 0 0? Yeah, plus 0 0. Then it will apply this. then it will apply 0 0 0 0 0 0 कहाँ है आपका ये 0 0 0 है, then it will apply 0 0 0. Okay. I should use different color pen. First vector plus minus minus is applied, okay, then plus 0 minus is applied, उसके बाद ये apply होगा, then plus 0 0 is applied, I mean this is applied, and then 0 0 0 is applied in one subcycle. In another subcycle I say reverse order में, see first this, then this, then this, then this, a reverse order में first this, then this, then this, then this. ठीक, right. आपका suppose rotating reference vector is somewhere here. This is, say for example it is in region 1. इसको मैं region 1 R1 call करूँगा. It is in region 1. Okay. My rotating reference vector is in region 1. So therefore, when null vector 0 0 0 is applied, what is the error? This is what we desire. This is the desired rotating reference vector, but this is what we apply. So this is error voltage vector. ठीक? When plus minus minus is applied, plus minus minus ये है. This is your reference rotating vector and this is what you are applying. So ये error vector है. When this plus 0 minus is applied, plus 0 minus, this is what is desired and this is what you are applying. ये error voltage vector है. And then, okay, plus 0 0, plus 0 0 ये है. This is what you are what you desire, and this is what you are applying. ये error voltage vector है. So when this vector is applied, error voltage vector is very small. When this vector is applied, again error voltage vector is small. When this voltage vector is applied, error voltage vector is again small. But when this null vector is applied, error voltage vector is large. Okay, this is for out of phase level shifted PWM. Let us consider now a switching sequence for in phase. Okay. I'll write here switching sequence for in phase level shifted carriers. Level shifted carriers. So we again have two carriers, level shifted but in phase. Okay. So ये plus है, plus 1 है, positive peak. Okay, this is 0 and this is minus Vp. Okay. अब मेरे पास दो carriers हैं. I will take half of the carrier period. ये एक, sorry, ये एक है और दूसरा भी ऐसा ही है. That also is, that is level shifted but in phase. अब आप clearly देख सकते हैं, this is carrier 1 and this is carrier 2. Half cycle में ले रहा हूँ, half carrier cycle. This is again one subcycle, TS, half carrier period. C1, C2, and these are level shifted. ये 0 to plus 1 change हो रहा है, ये minus 0 to minus 1 change हो रहा है. So level shifted but in phase. You can see they are, इससे पहले हमने out of phase दिखाया था, एक ऐसे एक ऐसे. Now these both carriers are in phase. Now these carriers have to be compared with modulating waves. ये मेरी modulating wave MR है, right? Correct? This is the modulating wave MY, for example, and this is my modulating wave MB. Let us see the switching sequences. Start from here. Phase R, phase Y, phase B. पहला intersection यहाँ पे है. This is the first intersection between carrier and this modulating waves. Carrier intersects with MB. Now you can see during this interval, MR is greater than both the carriers, so R has plus status. What about MY? MY is greater than carrier 2, but it is less than carrier 1, so it has a status of 0. What about MB? MB is also, it is greater than carrier 2, but less than carrier 1, 0. So ये पहला है, right? Where is the other intersection? Other intersection is here. ये दूसरा intersection है. This is the second intersection. carrier 2 is intersecting with My. Now you can see during this period Mr is again greater than both the carriers, so R phase has positive status. My is greater than C2 but less than this, so 0. And MB, you can see MB is less than both the carriers, so minus. That means bottom two switches of phase leg B are on. तीसरा intersection ये है, immediately इसके बाद तीसरा intersection. During this period, we can say MR is MR is again greater than both the carriers. So plus, what about MY? MY is greater than, MY is also less than both. Sorry, let me check it. MY is, कहीं गड़बड़ तो नहीं हुई है, plus 0 0 plus 0 minus plus, let me check it, plus 0 0 plus 0 minus. I've already drawn it on the rough. I will just check it. 0 0 minus. Yes. Yes. Here, yes, it is MR is greater than this, both the carriers, plus, what about MY? MY is less than both the carriers, so minus. And what about MB? MB is also less than both the carriers, minus, plus, minus, minus. Okay. And finally, we have this period. During this period, MR is now less than this carrier but greater than this carrier, so 0. My is less than both the carriers, minus. MB is also less than both the carriers, minus. So let us write the switching sequence. So switching sequence is plus 0 0 followed by plus 0 minus A, followed by plus minus minus, followed by 0 minus minus in one subcycle, TS. Right? And in another subcycle, it is in another subcycle, yes, it is like this. Ulta, 0 minus minus, followed by plus minus minus, followed by plus 0 minus, and followed by plus 0 0. ये दूसरा subcycle है, yes. Let us see it from space vector diagram. Okay, our space vector diagram in sector 1 would be like this. यह आपका space voltage vector with switching sequence plus minus minus है. ये space voltage vector है plus plus minus. ये है plus 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 0 0 0 minus 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 null vector. And this is your plus 0 minus space voltage vector. This is plus 0 0 plus 0 0 and this, and plus 0 0 and 0 0 minus plus 0 0 0 0. Is it plus 0 0 0 0 minus? Let me check it. Plus 0 0 0 0 minus. Excuse me. Yeah, it is here. Plus 0 0 0 minus minus. Sorry, 0 minus minus. और एक वेक्टर आपका यहाँ पे है, which is plus plus 0 0 0 minus. Okay, right? यह आपका आपके regions है. Okay, switching sequences plus 0 0. So you start from here. You first apply active vector plus 0 0. Then you apply active vector plus 0 minus A. So you move along this. Then you apply plus minus minus, ये vector. Then you apply 0 0 minus, वापस ये vector. खत्म. That's it. ये पहला vector. I repeat, plus 0 0. Here you apply it for time interval t1. It's also called pivot vector. ये जो corner पे vectors है, these are called pivot vectors. Pivot vectors. This is pivot vector. So first you apply pivot vector plus 0 0. Then you apply plus 0 minus. Where is plus 0 minus? ये भी pivot vector है. So you apply two pivot vectors. Because its amplitude is VDC by 2. This is VDC by 2. This is VDC by 2. Whereas this vector has an amplitude of VDC. Anyway, first you apply plus 0 0. Then you apply plus 0 minus. So for some time, then you apply plus minus minus. Move here. Then you apply 0 minus minus back. ठीक है. और आपका reference vector, it will be in region 1. ये आपका region 1 है. It's somewhere here. ये vref है आपका reference vector. But when this vector is applied, very small error VR is produced. When this vector is applied, very small error is again produced. When this vector is applied, very small error is again produced. So you can see very small error is produced when the three vectors are applied. I mean, when this is the switching sequence. Okay, a very small error is produced. What does that mean? That means it produces better harmonic spectrum. Better harmonic spectrum. I had made some statement somewhere that the in-phase carriers will give very small error and hence low THD. Okay, low THD in-phase carriers. You can say we have in-phase carriers. It gives, maybe by mistake I have given a statement few minutes back or half an hour back that out of phase level shifted carriers give better harmonic spectrum. That's not true. In phase carriers give better harmonic spectrum, because out of phase में अभी आपने देखा null vector 0 is also applied, and when null vector is applied, error is very large, because this is your reference vector and this is error. Here we are not applying null vector, we are applying these three vectors, which is called nearest three vector, NTVs, nearest three vectors. So therefore, when you are using in phase level shifted carriers, you are using nearest three vectors. For example, when your reference vector is in region 1, what are the nearest three vectors? ये nearest three vectors. अगर आपका reference vector region 2 में होता, R2, using in phase level shifted carriers, it would have applied these three nearest vectors. और ये vector और ये vector और ये vector apply नहीं होता. When it would have been in this region, say region 4, then these nearest three vectors it will apply. And if it is in this region, say region, you can call this region 3, it applies these three nearest vectors. So in phase level shifted carrier sinusoidal PWM gives, it applies nearest three vectors. Your reference vector may be in any one of the 4 regions, and in a particular region it applies the nearest three vectors which belong to that particular region. For example, you have seen your reference rotating vector is in region 1 right now, and it is applying these three nearest vectors. It is not applying any vector which is outside this region 1. It's not applying this, it's not applying this, it's not applying this. So that way you can see these errors are very small. So it gives better harmonic spectrum. So therefore I may change my statement. Few moments back I had made a statement that out of phase level shifted carrier PWM gives better harmonic spectrum. No, that is wrong. क्योंकि अभी थोड़ी देर पहले हमने देखा उसमें when null vector is applied, 2 vectors are applied from a particular region and 1 vector is outside region, and that gives large error. So that means Sine PWM or Sine Triangle PWM with in phase level shifted carriers give better harmonic spectrum. Please correct the statement if I have made a statement that out of phase level shifted carriers give better harmonic spectrum. That is wrong, because we have proved through space vector diagram that in phase level shifted carriers give better harmonic spectrum, because these errors are very small and nearest three vectors NTVs are used. So sine triangle PWM with in phase level shifted carriers give better harmonic spectrum than out of phase level shifted carriers than out of phase carriers. So it uses the concept of NTVs, nearest three vectors. Your reference vector at any instant of time may be in any one of the four regions. So in sector 1 or in any other sector, it may be in any one of the region. And when it is in a particular region, it applies the nearest three vectors of that region. It does not apply any vector outside that region, and it produces very less error and better harmonic spectrum. I hope this is clear to all of you. Okay. Now, in a similar way, we can, this is Sine Triangle Pwm. So the conclusion is that Sine Triangle Pwm can be very easily implemented for 3-level voltage source inverters or neutral point clamped NPC inverters by using level shifted carriers. Now we have two options, either to use in phase level shifted carriers or out of phase level shifted carriers. We have found from the analysis of switching sequence that Sine Triangle Pwm with in phase level shifted carriers give better harmonic spectrum than Sine Triangle Pwm with out of phase level shifted carriers, because the in phase level shifted carriers use nearest three vectors at your rotating reference vector maybe in any of the regions, and depending upon in which region the reference vector is, it applies nearest three vectors and gives less error. Okay. Now after this we will go for addition of common mode signal. Addition of common mode signal. Just like 2-level voltage source inverters, in 3-level voltage source inverters also we may inject a third harmonic component or third harmonic signal. Third harmonic component, we're giving third harmonic injected PWM. Third harmonic injected PWM. Okay, this third harmonic component is added to all the three sinusoidal modulating waves, and we may also use, we may also use third harmonic or triple frequency components, not the third harmonic component, triple frequency component which will have third and multiples of third harmonic, which will give bus clamping PWM or discontinuous PWM. Just in the same way we have done for 2-level voltage source inverter. Bus clamping PWM or discontinuous PWM. Okay. I will make one more statement, that is in 2-level voltage source inverters, a particular phase leg is clamped to either positive DC bus or negative DC bus using bus clamping PWM technique, BCPWM, bus clamping PWM. Whereas in 3-level voltage source inverter, in 3-level voltage source inverters, a particular phase leg gets clamped or is clamped to either positive DC bus or negative DC bus or DC bus neutral. DC bus neutral is another possibility, giving zero voltage output voltage using bus clamping PWM technique. Okay, so in 2-level inverters using any bus clamping PWM technique, whether it is continual clamp PWM or split clamp PWM or 60-degree clamp PWM or 30-degree clamp PWM, a particular phase leg is clamped to either positive DC bus or negative DC bus. Whereas in 3-level voltage source inverters, if you use these bus clamping techniques, a particular phase leg may get clamped to either positive DC bus, giving a pole voltage VRO equal to VDC by 2 during the clamping period, or it may get clamped to negative DC bus giving pole voltage equal to minus VDC by 2 during the clamping period, or it may get clamped to DC bus neutral giving zero pole voltage for clamping period. So this is the difference between bus clamping of 2-level inverters and bus clamping of 3-level inverters. Let me quickly discuss with you third harmonic injection PWM in 3-level inverters. Third harmonic injection PWM technique in neutral point clamped or 3-level voltage source inverter, or we can write 3-level or NPC inverter. Okay, it's something like this. It's very simple as in 2-level inverters. So we have for example, we have original sinusoidal modulating wave MR 0.8 and maybe minus 0.8. Okay, this is one positive peak of the carrier, and this is negative peak of the carrier, minus 1 minus VP. And we will take in phase. Just few moments back we have come to the conclusion that in phase level shifted carriers give better harmonic spectrum than out of phase level shifted carriers. So let us take in phase level shifted carriers. 1, 2, 3, 4, 4, and 1, 2, 3, 4. Then in phase will be like this. I'm taking less number of carrier cycles for better understanding. So it is like in phase, level shifted. Drawing errors, drawing inaccuracies are regretted. So this is carrier C1, this is carrier C2, and they are level shifted but in phase. This is original modulating wave. Now with this original modulating wave, what we are doing, we are adding third harmonic component. And when that third harmonic component is added to MR, we get the modified modulating wave like this, something like this. You already know it. We have studied it in 2-level voltage source inverters. It's simple. It's similar to that. So this is my MR star. And it will produce 15.5% higher inverter output voltage for K equal to 1/6 and best harmonic spectrum for K equal to 1/4. That remains same. That does not change. Okay. So switching sequence is something like this. Let me quickly show you switching sequence. Switching sequence. This is plus, this is 0, and this is minus. This is one carrier, in phase carrier we are taking. So this is our original MR, for example. Original modified modulating wave MR. Okay, this is original modified modulating wave MY, and this may be original modified modulating wave MB. When you add common mode signal, what happens? The signals, MR, MY, MB, they either get shifted above or below at any instant of time. Let us assume that all the three modulating waves become MR star, it's shifted above. This is MY and this is MY star. It's also shifted above, and this is MB or Mira MB star. Yeah, modified modulating wave after third harmonic injection. Then, R, Y, B. Switching sequence is almost same. ये पहला point of intersection है. Here during this period you will find MR star is greater than both the carriers, so plus. What about MY? MY is greater than 1 but less than another, so 0. MB is also, MB is greater than MB star. It is greater than this but less than this, so 0. Okay, right? Then उसके बाद ये दूसरी intersection ये है. Second intersection is this. ये दूसरा intersection है. During this period, MR star is again greater, so plus. my is greater than 1 but less than another 0, and mb star is less than both the carriers minus. उसके बाद ये intersection है, this intersection, ये this is another point of intersection. Excuse me, there is some error here. ये यहाँ है, this is somewhere here. This and ये यहाँ तक है, it's up to this, and then ये तीसरा है, this mr is less than this but greater than this, so 0, my is greater than, my star is greater than this carrier but less than this, 0, and mb star कहाँ है, it is less than both, minus. और finally आपका ये है last. Okay, so it is again 0 minus minus. तो ये आपका switching sequence है. Okay, so we can quickly go to bus clamping PWM technique. I will discuss with you quickly 60-degree clamp PWM. 60-degree clamp, which is a special case of continual clamp PWM in neutral point clamped 3-level inverter in NPC inverter. Okay, so we'll again draw waveforms. So this is 0.8, this is minus 0.8, और मेरे carrier I will take in phase carriers. It's 1.0 minus 1.0. In phase level shifted carriers 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Or in phase carrier level shifted carriers. This is carrier C1, and on the bottom side I will draw carrier C2. It's in phase with this carrier but level shifted also. C2. Level shifted in phase carrier. Drawing inaccuracies are regretted because I am drawing these in a very hurry. I want to finish it today only, so that's it. Bus clamping will be done like this. Okay, 60-degree clamp means यहाँ से यहाँ तक आप clamping करेंगे 60 to 120 degrees. So your modified model, this is your actual modulating wave, MR. ये आपकी actual modulating wave है. A modified modulating wave will become something like this. If you remember, you know how to generate that. You have to add common mode signal. ऐसी common mode signal आपको add करनी है to all the 3 modulating waves, and you will get modified modulating wave. For example, MRs. This is your MR star, like this. Okay. This I have already explained in quite details in 2-level inverters. It will remain same for 3-level inverters also. Sorry. So this is 60-degree clamp. Yes, 60-degree clamp. This MR star from 60 degrees to 120 degrees. Phase leg R is clamped to positive DC bus, and for 240 to 300 degrees, phase leg R is clamped to negative DC bus. Similarly, you can show it for other phase legs. So it is exactly similar to what we have achieved, what we have discussed in 2-level inverters. No difference at all. Okay, what about switching sequence? Switching sequence will be different from normal switching sequence. Switching sequence. For example, this is plus Vp, this is 0, and this is minus Vp. ये आपका एक कैरियर है और ये आपका दूसरा इन फेज कैरियर है, राइट? और MR आपकी ये है बिकॉज फेज लेग और यू आर क्लैम्पिंग टू पॉजिटिव DC बस. ये आपका MR है. दिस इज योर MR. MR amplitude is equal to peak of the carrier wave. So it has same peak as carrier wave. So this is your MR star. What about MY star? MY star is maybe somewhere here. This is MY star. And this may be your MB star. Now see the switching sequence. यहाँ से यहाँ तक पहली switching है और यहाँ so यहाँ तक, this is the second switching and this is the third switching. Now this is phase leg, phase R, phase Y and phase B status. During this period, you can see MR star is greater than both the carriers, so it has a status of plus. What about MY star? MY star is greater than this carrier but less than this carrier, so it is 0. MB star is greater than this carrier but less than this carrier, so less than this carrier, so 0, plus 0, 0. दूसरे में भी ये plus continuously होगा because phase leg R is clamped to positive DC bus, so R will have plus 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 all throughout. So plus. What about MY star? MY star is again, greater than this carrier but less than this carrier, 0. MB star is now less than both the carriers, minus. और उसके बाद तीसरा, it is again plus, R phase is again plus. Y is greater than 1, MY star is less than both the carriers, minus, and this is also less than both the carriers. Therefore, switching sequence is like this. For 60-degree clamp PWM, switching sequence is plus 0, 0, followed by plus 0, minus, followed by plus, minus, minus. Reverse order में plus, minus, minus, followed by plus 0, minus, followed by plus 0, 0. तो ये आपका sub-cycle, one sub-cycle, and this is another sub-cycle. I can show you in space vector domain. This is vector with switching sequence plus, minus, minus. This is space vector with switching sequence plus plus minus. ये आपका तीसरा vector है यहाँ middle vector with switching sequence plus 0 0 और 0 minus minus. ये है plus 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 null vector 0 0 0 और minus minus minus. ये middle vector है यहाँ with switching sequence plus 0 minus. ये आपका एक और middle vector है यहाँ with switching sequence plus plus 0 और 0 0 minus. Okay. और ये आपके 4 regions हैं. These are the 4 regions, R1, R2, R3, R4. Okay, first of all you are applying pivot vector plus 0, 0. ये pivot vector plus 0, 0. You are applying, followed by plus 0, minus. Where is plus 0, minus? ये. And this is applied, followed by plus, minus, minus. ये हो गया आपका. So first you are applying this, then this, then this. Reverse order में first this, then this, then this. Reverse order में ऐसे, ऐसे. And therefore, obviously, your rotating reference vector will be in region, if this is region 1, it will be in region 2. And you can see it is again using the nearest 3 vectors, this, this and this. These 3 vectors belong to this particular region. No vector outside this region is applied across the load. So therefore, error at any instant of time will be much less than out of phase level shifted carriers. So this is how bus clamping is achieved in, in 3-level voltage source inverters. So that's all. I think I should call it a day. That's all about sine triangle and sine triangle PWM, third harmonic injection PWM and bus clamping PWM, जिसमें हमने 60-degree clamp PWM discuss किया for 3-phase, 3-level or 3-phase NPC voltage source inverter. Okay, as far as space vector for 3-level inverters is concerned, I have given you some idea about the space vector diagram, but space vector in 3-level inverters or multi-level inverters will be discussed by Dr. Tabish in much details. So I would advise all of you to go through this lecture and also listen to or also watch the lecture delivered by Dr. Tabish Nazir for space vector implementation or space vector PWM for 3-level or multi-level voltage source inverters. There are some very important references. I will display them on your screen, so you can go through these references. First reference is by D. Banerjee, Rajesh Ghosh, V.T. Ranganathan and G. Narayanan, comparison of various sine triangle PWM techniques for 3-level voltage source inverters in space vector diagram. This was published in National Power Electronics Conference NPEC in IIT Kharagpur in December 2005, followed by second publication, this space vector based analysis and comparison of sinusoidal pulse width modulation schemes for a 3-level inverter, and then study on pulse width modulation techniques for a neutral point clamped voltage source inverter. This is a PhD thesis from Department of Electrical Engineering, Indian Institute of Science, IISc Bangalore, July 2012. If you have access to this PhD thesis, those of you who want to pursue their research in this area, they can go through that research, go through that thesis. Okay, some more references are like this: study on pulse width modulation techniques for neutral point. Okay, this is same PhD thesis, and then a computationally efficient PWM algorithm for multi-level inverters. This was published in Proceeding First National Power Electronics Conference in IIT Bombay in 2003. So please go through this lecture and other lectures, and in case of any clarifications, any doubts. Okay, before I wind up the lecture, there are some more references for advanced bus clamping PWM technique for 3-level voltage source. When Dr. Tabish will teach you space vector in 3-level inverters, you can then yourself download these references and you can study advanced bus clamping PWM for 3-level inverter, not from examination point of view, but from the point of view of research in this area. First publication is by S. Das and G. Narayanan, Novel Switching Sequences of a Space Vector Modulated 3-Level Inverter, IEEE Transactions on Industrial Electronics. Another is by Soumitra Das, Study on Pulse Width Modulation Techniques for a Neutral Point Clamped Voltage Source Inverter, PhD thesis, again, Department of Electrical Engineering, IISc Bangalore. Please go through this lecture and other lectures. In case of any clarifications, any doubts, you are most welcome to put your queries on the WhatsApp group. I wish all the best to all of you. Thank you.